All right, welcome to the second talk of the morning session. It will be given by Professor Apoorva Patel of IISc, and he's going to tell us about quantum advantage in unsupervised machine learning.
So thank you for the invitation to give this talk. It has actually only a little bit of condensed matter physics, more on the quantum information theory side, but it is bringing into focus two topics which are very much in the news. And one of them is machine learning, and the other one is quantum advantage. The point I want to emphasize in this particular talk that the kind of statements which are in the news, you have to take them with a pinch of salt. There is exaggeration, and when you try to figure out what exactly is actually happening, things are restricted. So let me first give a little description of what is machine learning all about. It's essentially dealing with problems with big data. There are many different scenarios where sensors and detectors are picking up huge amount of data. You don't have time to analyze it. You basically quickly filter out something that is of interest to you and throw away all the rest. And the purpose is that you want to pick out something which will help you in making some decisions. It may be uncertain, it may be imperfect, but yes, it will guide you in some particular direction. And the examples are widespread in astronomy, satellite imagery, all kind of surveillance, weather, climate, internet traffic, all kind of model systems for design, observations running from condensed matter physics to high energy physics, and even biology. Huge amount of stuff is there. Can you make some reasonable extraction of useful information out? And it is a kind of situation where things are like use it or lose it. It depends on your capability. And to just give an examples, astronomers look at light from stars, galaxies, black holes, over the whole universe, and try to figure out something from it. But that light was there for billions of years, even when no astronomers were looking at it. What happened? Well, it just went. Nobody made any sense out of it. If you have the capability, well, you figure out something, but otherwise it is just going to go. And the purpose of machine learning is to figure out something that is useful. What are the kind of questions that are asked? Well, three problems are tackled. The first one, you can just call it pattern recognition. The data is there, you are trying to figure out some interesting stuff from it. After you found some pattern, you classify them, this type, that type, etc. And after classification, well, you talk about recommendation system. What can you suggest based on whatever you have seen? And these problems are tedious because of the huge data. So you give it to somebody who can work in the background and do your job, and that is typically a computer. And you have to give some rules to the computer because otherwise it will get lost. And three labels again are used about what the computer does in these scenarios. One of them is called supervised learning, which means that first you train the computer using a set of trained data. It will find some parameters and then use it later to classify or analyze the new data which comes in. There is something called reinforcement learning, where the computer is given some rewards in some sense, that yes, you did it right or you did it wrong. So whatever was done right, well, gets an advantage, and the other stuff that you didn't get it right, you throw away. So the computer kind of narrows down the choices in some particular manner. And the third thing is unsupervised learning, where actually you don't have a model and you just have some similarities and analogies. And based on the analogies, the computer is supposed to build up a system for you. And there is a fancy name for this thing, which is called artificial intelligence. So what I'm going to talk about is actually this last stuff. And to deal with this, there are no ready-made rigorous results. People use typically neural network methods heuristically. If it works well, well and good. If it doesn't work, try something else. And that is the state of the subject. So what is this particular topic of unsupervised learning? It is to find the probability distribution of the data generated in some scenario. And that probability distribution, if you figure out, you can make predictions based on it. How are you going to find the probability distribution? By some guess, where some related stuff is given, so there is some analogy, and you can say that this looks like that, so maybe it is in this particular category, and then you improve it by trying to fit the data in a better manner, and things progress in that particular manner. How do you improve it? Well, you have to figure out how you differentiate or categorize two different probability distributions. And for that, there is a well-known quantity called Kullback-Leibler divergence. It is actually the relative entropy of two particular distributions, and is defined by this straightforward looking distribution. One of them is P of X, another one is QX. And what it measures, that it is the amount of information lost when PX is used to approximate QX. It's asymmetric in PX and QX, but that is fine because it is always non-negative and it vanishes only when PX and QX coincide. So you can actually use it to minimize towards the direction in which you want to go. And what is done is data has some Q of X. You parameterize P of X in some manner and then minimize this divergence. So that is what the typical algorithms in unsupervised learning do. The name which appears in connection with unsupervised learning is Weizmann machines. How did Weizmann appear in this analysis is based on the kind of simple guess that most of the probability distributions which we deal with, they come from some physical process. And if that is true, then you expect that the probability distribution is given by e raised to minus beta times some Hamiltonian divided by the partition function. And you can then try to understand how that particular distribution got created if you have a good guess for the Hamiltonian. It also happens that most of the time you don't have access to all the degrees of freedom. So you have to perform a partial sum over all the degrees of freedom which are not observed that produce reduced probability distributions. And in the neural network, these unobserved degrees of freedom are called hidden variables. So what are the kind of Weizmann machines we are used? Well, the Hamiltonian is written in terms of the simplest systems which are used in condensed matter physics, some spin glass, where there is an interaction between different spins with a strength Wij, it varies, it's not a constant. And there is a kind of bias field, which is again varies from place to place. And you put both of them together. And what is done in this Ising spin models, you start from a high temperature system and then gradually drive it down towards this equilibrium state, thermal equilibrium state, by the process which is essentially simulated. So you model this Boltzmann machine by this kind of a system and see whether such a model will have any use in explaining your data. There are further caveats.
WI typically will have a range.
Yeah, they are typically range, but they are not constants. They fluctuate. They have changes in signs also. Some of them will be positive, some of them can be negative. That's why it is a spin class. So this turns out to be too general, too many variables, and it goes all over the place. And when you try to put it in a computer, you don't get anything simple looking. So people put constraints on this. So there is something which is called a restricted Boltzmann machine, where the connections, this Wij, exist only between the observable degrees of freedom and the hidden variables, but no connection among the observables and no connection among the hidden variables. So it's a kind of layered structure. You have connections going from one side to another, but no connection on this side or no connection on that side. And this turns out to be more useful in modeling the system because it avoids all kind of unnecessary interactions and does a little better job in explaining certain types of data. And then there are something called a deep Boltzmann machine, where there are multiple layers. One layer of observables, one hidden layer, another hidden layer after that, etc. And they have been popularized quite a lot in the neural network analysis. So this is just a kind of terminology. And now let me jump to the quantum part. You don't have to worry too much about the neural network details to understand the quantum part. So what are you going to do when you replace this statistical mechanics by quantum mechanics? It's easily done in the language of the density matrix, that any expectation value, which is average over some probability distribution of some observable, can be written as trace of rho times O. Density matrix is a generalization of Px, so there are only, say, n component over here. This will become n times n matrix, so it has n square degree. Rho is always positive semi-definite, so it can always be written as exponential of Hamiltonian if you want. There is no problem with that. And the reduced probability distributions, which are used for calculating the sum over the hidden variables, well, no problem with that in constructing the density matrix either. But it's a more powerful system because there are lots of variables sitting inside and you have extra freedom in parameterizing them, changing them. The question is, will you gain anything by going into this more general language? And here comes a very simple observation. Yeah, first of all, I can tell you that the relative entropy has very straightforward generalization also with the same property. It is non-negative and vanishes only when the two distributions coincide. So it can be used to calculate gradient and go towards the minimum. But the new feature which appears here, that rho and O don't commute in general. When they do, you can go to a basis where both of them are simultaneously diagonal. And so this description will collapse to the classical. From n square degrees of freedom, you will just go on to n degrees of freedom. And in that case, there is absolutely no advantage in going to the quantum language. So in fact, the commutator of rho and O being non-zero is a necessary condition for obtaining quantum advantage. If that is not true, then you will just use the classical model. There is no need to complicate your life and going into a quantum description. And this feature is kind of peculiar because the advantage depends on the observable that you are trying to measure. There is no analog of that in the classical system, where once you have a probability distribution, you just calculate whatever observable you feel. But this is a more restricted case that some observables, the classical thing will work very well, but there may be some other observable where the quantum description will give you an advantage. And then one can ask a simple question: is there a bound? And the easy guess is that, well, quantum advantage would be the largest when the commutator is the largest. You can actually solve this problem for the simple reason that the density matrix is bounded and operator norm can be fixed by some convention. So that gives a very specific criterion about when the quantum advantage will appear in your analysis, and that is the result I am going to explicitly describe. How will you deal with this on a computer? Well, you can always define a basis in which the density matrix diagonal, another basis in which the operator is diagonal, and the two bases are related by some transformation. You can choose a language that I can say that the U describes the basis which will have operator diagonal and the row will be non-diagonal, or vice versa, that I will transform the density matrix by a certain operator and go to the basis in which O is diagonal. So you can deal it with either way. And the way it is generally done in computer simulation is you take a fixed basis of the operator because that is what you want to measure, you diagonalize it, and then somehow evolve the density matrix so that you minimize or maximize certain quantity, which gives you an advantage. And the evolution of the density matrix, you can do it in many ways. A typical thing is you use some Hamiltonian for evolution. One has an easy way to calculate these traces on a quantum system by taking a expansion in what is called a polybasis. The advantage of the polybasis is that the operator is just a tensor product of polymatrices, and so any polybasis component will square to identity. And that allows you to simplify the whole analysis for measurement of a polybasis operator to just a simple operation of control O acting on the density matrix and a simple measurement. So that is not too complicated if you want to calculate any trace, if you want. The problem now can be explicitly described, and the simplest example is that for 1 qubit. I can take the basis for measurement of the O as the Z basis, and I'm free to play around with the density matrix. When is the commutator of rho and O maximum? Well, the density matrix is identity plus R dot sigma. Operator is in the Z basis, and so the commutator will maximize when R is in the equatorial plane, some combination of sigma x and sigma 1. The explicit solution, there is nothing more that you can play with. And so how will you deal with this situation? Well, you have a Z basis as a reference frame for the operator. You can get this rho by applying just a pi by 2 pulse in a transverse direction. Transverse direction is in the equatorial plane. And then you get a density matrix which has a largest commutator. And this is a strategy or idea which people are playing with, and it converts this Hamiltonian to a transverse field Ising model from the spin class. This is the interaction which couples the various spins. They are diagonal in the operator measurement basis. And this interaction in the transverse field flips it depending on the strength from the Z basis to something which is a combination of X and Y. And this is again a guess. People do this kind of thing and try to find out whether there is any advantage in using this particular density matrix to calculate certain observables. But this is too naive, and I can give some reasons for it, that if you are now looking at this commutator to be maximized, well, it will be maximum when the radius vector becomes 1. That is on the surface of the Bloch sphere. That happens to be the pure state. What does pure state mean? That the system decoupled from the hidden degrees of freedom. And that is actually not a neural network model. It is just a system by itself. So the advantage is there, but it is there for pure system. You put too many hidden variables and convert this into a mixed state density matrix, advantage actually goes down. What else? Well, you can solve this problem in general, not for a qubit, but for n by n matrix. Simple steps. First thing is the commutator only depends on the traceless parts. So I don't have to worry about the identity component at all, and worry about the traceless parts of the two Hermitian matrices, both rho and O are Hermitian. And they can be easily described by the Cartan generators of the diagonal structures. And the question is then, what is the configuration of these Cartan generators which will produce the maximum commutator? Well, the one component problem is what I described as a qubit. If there are only two numbers here, 1 and -1, we had as a simple solution, which is sigma dot n, and n is a direction which is transverse to the two components. And one can work out the maximum also, which gives this normalization as a quantity which depends a little bit on n. What in more general, that even a more general case can be solved essentially with the same result, that you have some entries which are positive, some entries which are negative, the trace is 0, so the sum of all the positive quantities and the sum of all the negative quantities can be rather trivially related, and the numbers of the positive and the negative terms don't have to be equal, they just have to add up to n. So rather simple situation. And now you can ask, when will the commutator be maximized? And it can be shown without too much trouble that it is maximized where all of this positive quantity collapse into one component, all of the negative quantity collapse into another component. T can be any one of these p directions, and minus t can be any of the two directions, and then it just looks like this two component solution, which is already known, and the formula essentially is identical. So that actually gives a general solution for arbitrary n by n matrix. The structure remains the same, and the solution is again something which can be easily said that I will have maximum commutator when the state becomes a pure state. So you are not going to get too much out of quantum theory compared to what is already achievable in classical theory. If you are going to use all these neural network models, most of the advantage of the neural network model is in the classical physics itself. And little bit you can get, but that will depend very much on what the definitions of density matrix and the observable that you are trying to measure. In some sense, this gives an upper bound. How much is the quantum advantage? Well, this is as much as is available. And after that, it's kind of a trade-off. It's only so much is available. Are you willing to invest extra effort of going into a quantum system? Well, it is worth it, you will do it. If it is not worth it, you won't worry about it. So this is essentially the whole analysis of the problem which I did. There are certain other things which are available in analyzing the large data, but they go beyond this machine learning formalism in a certain sense, and I just point them out. One of them is that the mapping, which is often used between data in one representation from the other one, it is called a feature map. And the feature map which are available in quantum information theory, they are much more powerful than those available in classical theory. So there are certain feature maps which are exponentially hard to construct classically compared to a polynomial effort required in a quantum language. If the data sets are of this type, well-known example which has been rigorously analyzed is the discrete logarithm problem. If your data set falls in some particular type of this, which involves these feature maps which are naturally finding its place in a quantum dynamics, well, you can do things which classical physics will not allow you to. The other feature which has been again rigorously shown is the data may come from a quantum process. The underlying process is quantum. You can use that data directly from machine learning without intervening measurements which will project this quantum data into a classical set. If you give up that intervening measurement, take the quantum output of the device, feed it into a quantum computer to analyzing it, there are coherent correlations which will survive. And these correlations can provide an exponential advantage. It can be rigorously shown as by these people. And that is a scenario where all this analysis using quantum computers is probably going to be most helpful. You are trying to study a quantum system, don't convert it to a classical language, just directly analyze the quantum data, and then you will get a new kind of phenomena, or rather you will be observing new kind of phenomena much more efficiently. There is a disadvantage which I'll want to mention because it is kind of routine, that once you go to the quantum domain, everything becomes probabilistic in general. So a single experiment is not going to give you the final result. You will have to repeat it multiple number of times to get sufficient accuracy. This you cannot bypass. So you have to keep that in mind, that you will have to run the experiment multiple number of times on identically prepared states. If you have that particular luxury, well, there is things to be gained into going into quantum domain and applying a quantum algorithm. Thank you.
Questions?
I'm reading from this screen, the second paragraph. When the input data originate from quantum process, they may be directly used for machine learning without intervening measurements. So I'm not sure I understand. I mean, if you have some data, then either you or the machine itself are doing some measurement on the state. So how can you use this without performing measurement?
Let me give an example. It's not really quantum, but simple enough to understand. Is what astronomers do in large baseline interferometry. The data which is kept is not only the intensity, but also the phase information. And in that large baseline interferometry, you have multiple data you combine, keeping in mind the phase information, and that allows you to detect features which you could not have detected just by looking at the intensity. So the complex numbers which are present in quantum dynamics behave the same way. You have multiple streams, but what you have is this coherent correlations. And if you keep that phase information, that allows you to gain something more than just keeping the normalization. And what happens in taking the measurement is you will keep the normalization, but the phase get lost, because when you measure, you get just the absolute probability and the phase is lost.
No, it's a question of what you measure, but I fully appreciate the fact that you can measure phase as well in certain experiments. But once you measure a given quantity, a given observable, then by the very nature of quantum mechanics, you have back action on the system. So you dramatically change the state of the system. For example, project it or do something else very dramatic on the system. So how can you? I'm not sure that I follow the logic of this second paragraph.
The final measurement will always be there, but what you are adding is the possibility of having interference between multiple data streams before you perform the measurement.
Other questions, maybe from a student?
Excuse me. So here, so is IISc building this dedicated Ising machines, I mean, in hardware, jointly with Accenture?
No, can you repeat? I did not understand.
And, is IISc building this special purpose Ising machine, which is a quantum Boltzmann machine, jointly with Accenture?
No, IISc is not building a Boltzmann machine in the conventional sense. The Boltzmann machines which people are describing are actually just classical computers. And what is called Boltzmann machine is actually the software code. You're not directly.
No, I'm not saying, I mean, we can build a hardware which is a special purpose Ising machines. So like, which is a like partial quantum computer in some sense.
Well, in principle, yes, but I don't think anybody has built anything similar. I mean, people have talked about it, there is no doubt about it, but nobody has built it so far.
Any further questions? If not, let's thank Professor Patel and both the speakers. Session.